This is a whole number. If you have A is the nuclear number, it's the number of protons, number of neutrons. And you know how to do this. So how big is a nucleus about compared to the atom? The atom is about in centimeters. 10 to minus 10 meters, and the nucleus about the radius of it. 10 to minus 15. 5 orders of magnitude difference. Okay. So in order to determine masses, we take a mass spectrometer, and I have explained this to you. We have a sample, and we rip off an electron off the sample. We ionize it. Okay. Now I have a positively charged atom with one electron missing, and I call this an ion. And that ion, I can now accelerate by having a negative charge, and the charge attracts that positive ion. And I have an electrode here, which is hollow. So I accelerate it, and then it flies through. When it comes, I switch it quickly off, and it flies right through. Okay. Now I have a moving ion with mass, as mass and velocity and charge. And things like this will be deflected in a magnetic field. And if they are moving very fast, or if they are very small, the deflection is not as much, is not very much. If they are heavier, or moving very slowly, then the deflection, no, it's opposite, sorry. If they're moving fast, and if they're light or move fast, the deflection is very strong. If they are heavier or move slowly, the deflection is not as strong. So let's have a look at this. You have here, that's our light baby here. And so at the end, I have a detector. That means it gives me a signal. I said, aha, this is mass this. I've calibrated this. This is that mass number. And the intensity of that thing, how high that signal is, what does it give me? How many I have of this, okay? So now I have this heavy ion here. No, I don't have an ion. I ionize it here. Rip off the electron, accelerate it. And there I have that signal. I don't show you the intensity here. Of course, if it comes on and on and on, it will register every time it comes, and it will add it up, and it will get this intensity peak. If you have more of those. If I have 10 of those and one of those, it will have the same mass than here and here, but here it will be 10 times more intense than here, because every time I measure an electrical impulse, and I sum these electrical impulses up. So this is a rudimentary mass spectrometer. Of course, in the real world, they're extremely sensitive. They can do billions of the mass they can measure. Yeah? And so you have here, this is our mass scale now here. That mass 1, we know what mass 1 is, can be hydrogen. Yeah? Mass 2, what could that be? Heavy hydrogen, or a hydrogen molecule, it has one electron missing. Or at mass 3, what could that be? A helium-3, okay? Or mass 12, what is that? Carbon. And what's carbon? Carbon 12. Mass 13, what would that be? 13. And mass 16, what would that be? Oxygen. And mass 18? What? Oxygen 18. Or? H2O would be 18. Would it be oxygen 18 or H2O 16? We have 1 16 and 2 H's. What's mass 32? Oxygen molecule. Okay? Or 34 was an oxygen molecule, 1 with 16, 1 with 18. Or an oxygen 18 molecule was mass, what would that be? 1, 2, 3, 4, 5, 6, 36, okay? What is important for you is that you need to know is mass 44 is CO2, because these are results or products of combustion of hydrocarbon. Hydrocarbons have carbon and hydrogen, okay? And when you combust them in oxygen, the carbon becomes CO2. So each carbon makes one CO2 molecule, and 2 hydrogen in the compound make 1 water. So the mass of the water is 18, and the mass of the carbon dioxide is what? 44. So you have an mass 18 to mass 16 ratio. And from this ratio, you can get the empirical formula of your compound, of the hydrocarbon. Because if you take hydrocarbon and you burn it in oxygen, you make water and carbon dioxide. Yes? Yeah, sulfur, excellent. Can be sulfur. It would be not exactly 32. It would be 32O66 if you have, there's a sulfur isotope probably. Okay? Yes, you're right, absolutely. This is just a rudimentary scale I gave you. There's many other things that you can fill in there, but I don't have time for that. And so the empirical and molecular formula, the empirical formula you get from that ratio. So if you have methane, how many carbon dioxides do you make? 1. And how many waters? So what would be the 18 to 44 mass ratio? 18, you make how many waters? 2. And how many carbon dioxide you make? 1. You have to have carbon to make carbon dioxide. You make 1 CO2 and 2 H2O. So 1 CO2 and 2 H2O means that would be double as high. That would be the 44, and this would be the 18. Let's see how do you see that. That would be the 18 here, and that would be the 44 for you, okay? Double as high. Which one is double as high? The water, exactly. Intensity is double, okay? Now, how many carbon and hydrogen waters would you get here? Ratio would be 1 to 1, okay? And this one you can figure out yourself here. And so you would have to have 2 to 1 ratio. This would be 2, and this would be 1, okay? So this is the molecular formula, of course, is a multiple of this, not always, but this you have to do it a different way to see how big is that molecule itself. All right. Now, then we talked about radiation at light, and I got to step on it. We know now that light can behave as a wave, but also as a particle. We call it a particle photon, okay? So it has how do you call this? P is what? Momentum. P equals what? M times V. Okay, good. You're helping me out here. So the wave has a frequency and a wavelength. If the speed of light, it travels with the speed of light, is frequency times wavelength, is the speed of light, is a fixed number, it's given for you. Now, if you have a short wavelength, which one is the high energy? 400 or 700 nanometers? Which one has high energy? E equals H times nu, okay? Or E equals C over lambda. All right? Good. I should stop saying all right. I'm sort of confirming what I say. Bad habit. So how do we know that we are talking about light? That light is actually a wave? We do a double slit experiment, and with this you have a diffraction and interference pattern of light. And so you have, can you do this with polychromatic light? No. Why not? Because you have all these wavelengths, so where there's for one, there's a minimum, or there's black, it's bright for the other one. Okay? So you would see everything bright. So you have monochromatic light, or you could also have electrons, and we know that electrons are particles, but they behave like waves. That's what we've been talking all about the last 3 times, the last 3 lectures. So they behave like waves, and when they behave like waves, they have constructive and destructive interference. If 2 waves constructively interfere, does the intensity go up, double, or increase as they interfere, or decrease? Constructive interference. Increase. Okay. 2 waves. Up, down, up, down, up, down, up, down, up. Okay? Up, down, up, down, up, down, up, down, up, down, up. Okay? So is it bright there or dark? Highest intensity here. Now I go here, up, down, up, down, up, down, up, down, up, down, up, down, down. Up, down, up, down, up, down, up, down, up, down, up. Is it dark or light there? Dark, exactly. Destructive interference. Destructive interference. All right? 0. So it's bright here, dark here, brighter here, bright here, bright here. This is the brightest spot. So the spot is actually here on the screen. This just shows you the intensity. The intensity has nothing to do with the wavelengths. It just tells you how much of it you have there. Okay? So we have wavelengths is like an orange and an apple and a banana. And if you have 1,000 oranges, it still doesn't become a banana, okay? So, all right, that's sort of how you can imagine. It's rare. You have a high intensity of oranges, but it still is not a different wavelength, okay? So visible light spectrum is from 400 to 750 or something. What is that region called here? Is that the high energy region compared to this one? The low energy region, exactly. And that's the low energy region, and this is, what is that? It's red here, and what's then here? Infrared. And then you have even longer wavelengths. Wavelengths are here, long wavelengths, up to the meter wavelengths or centimeter. Your phone has something like millimeter wavelengths. And so which one has the highest energy here? Is that 400 or lower even, yeah? But we only showed that one. This is blue, and what's that here? Purple, or something like this, okay? Good. And this is the ultraviolet. First it's violet, and then it's ultraviolet. First it's red, and then it's infrared, not ultraviolet. Infrared, okay? And so this is, you need to memorize this. Look it up in your book, okay? I don't give you that. So you have absorption and emission. There could be a continuous absorption. You've done this in the lab, okay? You did an absorption spectrum. So this would, and this would be an emission spectrum, okay? A continuous one. So this would emit light. First it has to absorb the light. Remember our mercury lamp? We heated it up, and it brought it in excited states, and then it came back down into the ground state and emitted that bright light, and the bright light was made out of 4 frequencies, so 4 wavelengths. And I've shown this to you, I'm pointing here, I've shown this to you, I had it on the screen here, at different colors, 4 different colors, but we only could see 3, and the first one was in the UV, and I put a screen here to see that. And so this was a emission spectrum. And so this is actually also an emission spectrum. Every light is an emission spectrum. It emits energy. You heat it up, bring it up there, and so this is most of the light. If you have a regular, what are they called, the regular incandescent lamp, if you have those, most of the energy is given off as heat, so you can't touch that thing. It's nice to put a little diffuser on there, have little drops of scent on there, and it makes it a nice thing in the room, but it costs a lot. Only 10% of the energy that you put in gets out as light. And so that's why we're using diodes now. They are very efficient in emitting light. LEDs, light-emitting diodes. Yeah? And also fluorescent lights have much better efficiency. So this is fluorescent emission. Okay? So you have here, this one would be missing here. If this would be an emission spectrum, an absorption spectrum, this would be missing in the spectrum of your visible light, if this is invisible. And this one would be, what would be emitting the highest one? Would that be a one? Yeah, you would here emit something here, and here this would be the strongest one here, actually. The highest intensity would be, this would be the emission spectrum. So you got this. And where does this come from? From n equals? Can this come from n equals 1? Can it emit from n equals 1? No. You gotta get it up in energy levels to n equals 5 or 10 or whatever, or 4, and then it can go down. Very often it doesn't go all the way to the ground state. It stops in the middle state somewhere, and then it goes again. But this is something which I don't require you to know. So we have also talked about that light behaves as a particle, and so that particle-wave relationship we have with de Broglie. So when it's a wave, you can have a wavelength. And for a particle, has mass and velocity, p equals m times v, is h over lambda. If you have a particle, you can calculate a wavelength. Or if you have a wavelength, you can calculate a momentum. So if you have the momentum, you can calculate a wavelength, and if you have a wavelength, you can calculate the momentum. But of course, if you have something else that quantum particles, so are you a quantum particle, sir? No, but I can calculate a wavelength. For you, it would be a tremendously small wavelength, would make no sense whatsoever. So you have, what is a quantum particle? Name me 2 quantum particles. Photon, electron, what else? Okay, large molecules, you think they're quantum particles or not? No, right, exactly. Hemoglobin is not a quantum particle, okay? So then we had talked about the photoelectric effect. There are metals, and if any metal that you have, you can dislodge an electron. You have to hit the metal hard enough, with high enough energy, to get it away from the nucleus, to dislodge it. So you use light. E equals h times nu. The energy of light is h, that Planck's number there, times nu is the frequency of the light. And this is the wavelength, 1 over the wavelength, essentially. So when you have the right amount of energy, then you can dislodge that electron. So you have to have the right wavelength to dislodge that electron. Now, you can just have enough to dislodge it, and then it doesn't do anything. That's not good, because you want to make this electron, your photocell, for example, when you walk in the door somewhere in the store, and there's a photocell constantly dislodges electrons, it measures the current, and when you go in there, you block the current, and then the bell rings. You're in the store. Okay? So coming back to my electron, that electron, now if you give it energy of a higher energy, a wavelength with higher energy, what happens to that electron? You have dislodged it, there's enough energy to dislodge it, and the rest of the energy goes where? It goes as kinetic energy. And if you give it more energetic light, or higher, not more light, higher energetic light, the kinetic energy has more, okay? In order to dislodge it, you need the initial energy that's specific for the metal. That's called the work function. And plus the kinetic energy that you want that electron to have. That's what the light energy has to have, okay? So this is obviously red. Red is that higher compared to red and green. Which one has higher energy? Green, okay? And green and blue and red, which one has higher energy? Blue, good. So this one has more kinetic energy because you need green to dislodge it. Red is not enough, and this is the kinetic energy, and you get more kinetic energy, all right? So you can, of course, for different metals, this is different. And so the photon energy is E equals h times nu. That's that energy here. And you can calculate the kinetic energy is the photon energy minus the work function. Or the total energy is the kinetic energy plus the work function. Okay, that would be the total energy. And so we did this. That is fine. All right, now let's do electrons. We're getting further. Electrons can also behave as waves. We have done all this. All right, so you know that. And then we have ground states. N equals what? Lowest energy level. Is the energy 0 or does it have a value? Value. Energy level 2. Energy level 2. N equals 2. Energy level 3. N equals 3. How many nodes? N minus 1. See, it makes all sense now. Now you can have, if you want something to absorb light, you have to put the right energy in there because each atom has certain energy levels it can occupy. All right? So you need to put the right wavelengths or right frequency, the right energy of light in there. Oh, it goes by itself. Oh, nice. Okay. It says speed up, Nietzsche. Okay? Good. So, no, let's go back here. So this one, blue fits and green fits and thank you. Red fits. And so, of course, when it's up there, it can also go down. But remember, this could also go down here, or this can go down from here to here. It can go from here to here. This is when I ask you going to the ground state. That would be the ground state, but you can have the first excited state, second excited state, and so on. So I've showed you that quantum particles have to make sense. A baseball is not a quantum particle, but a sodium atom and an electron and a photon. These are quantum particles. So now there was one question which had a lot of you had trouble, and it had nothing to do with understanding. The problem has to do with calculation. How many photons are needed to stop a sodium atom? And the momentum. Remember, the momentum was in this thing here. The momentum of the sodium atom was lambda was 0.06 nanometers. 0.06 nanometers. So what is? You have to have the momentum in one direction, and then you have photons with the opposite momentum in the opposite direction. So you calculate the amount. The energy, the momentum for one photon, and then you see how many of those you need to stop the sodium atom. So why don't you give me a quick, click in there quick. I want you all in here. Okay, everybody click in and I can give you the solution while you're clicking in. Okay, so P is h over lambda. So P is h over 0.06. Now, and the photon is what the wavelengths we have given you. This was on the table here. And this was h over 600, or 1 over 600. The more mathematically inclined of you, they would see 1 over 006, to 1 over 0.06 to 1 over 600 is 10,000 of those you need in order to do that. But you also can take the calculation, you get 16.67 h, and here you get 16.67 times 10 to the minus 4 h. You divide this here by this here is 10 to the 4. So you need 10 to the 4 photons of that wavelengths to counteract that momentum of the sodium atom for it to stop. Did you get that? Good. And this we have all talked about. All right? Yeah. All righty. So now one other question. Let's stop it. And let's do that question. Give me quickly your answer. Was this review helpful, A, B, or C? Or absolutely not would be D? Now you can do it, my friends. Everybody has to do with participation points. Huh? Okay, good luck on Monday. And I see you on Monday morning. Office hours 3 to 4 today.